Hi there, my name is Shivdat. Today we're going to be looking at Zeno's paradox, an important idea in philosophy that's been there since the time of Zeno of Elea, who lived somewhere in the 400s BC. And it's actually not just one problem or one paradox, but a series, a set of problems and paradoxes that Zeno developed basically to prove his teacher's idea. His teacher was Parmenides, who was famous for saying, "All is one," his famous quote. And things like motion, movement between A and B are actually completely illusions. So in an attempt to kind of prove this idea of his teacher, Zeno came up with a series of problems. We'll look at two of the most important examples he gave, the arrow paradox and the Achilles and the tortoise paradox. And we'll also look at some possible refutations over the years and the effect of the paradox today. Alright, so basically Zeno's paradox is the first one, perhaps the first known example of proof by contradiction, reductio ad absurdum, where you assume something and then prove it's false. And it's also widely held to be believed as one of the sources for the Socratic dialectic method. So let's look at what the paradox is. First through the Achilles and the tortoise problem. Basically the problem is as follows. Say Achilles and the tortoise have a race. Now, say the tortoise gets a head start of however much, say 100 meters. Now Zeno claims that Achilles will never be able to catch the tortoise, no matter how long the race is, no matter how long they run. Now clearly this seems on the face of it false, right? If you were to observe Achilles and the tortoise running, eventually would not Achilles catch up with the tortoise? Well, Zeno's argument is as follows, and I mean that it seems clear to us that Achilles would catch up and overtake the tortoise, but we must find a flaw with Zeno's argument, to be able to kind of, his argument seems logical and we need to find a flaw with it to see where it's going wrong and why observation is different. So what Zeno says is that, okay, so Achilles and the tortoise are running. Let's say the tortoise is at this point, right? Now Achilles is going to have to reach this point, right? However long it takes. So Achilles reaches this point. By that point, the tortoise has gone some distance further. Admittedly, not as much as Achilles had traveled in that time, but he's gone some distance further. So let's say now the tortoise is here. Again, Achilles is going to have to get to that point where the tortoise is, right? So Achilles gets to that point. But when Achilles does get to that point, once again, the tortoise has moved some distance further, right? Again, it will be admittedly less than what Achilles moved, but it's some distance further. And this argument can really carry on forever. Okay, agreed, every time the tortoise will move a smaller distance further, because the amount of time is reducing, but the argument can just be continued forever. So in other words, till infinity. And so in other words, Achilles will never catch the tortoise because Achilles always has to reach the point at what the tortoise was previously. And every time he reaches that point, the tortoise has moved a little further. And we can keep carrying out this argument. A second version of the paradox is as follows, which claims that an arrow will never reach its target. It's really the same problem, but it's kind of framed in a different way. So let's take a look at it. Supposing this was the target, and this is an arrow, right? It has to travel this distance. This is the target. This is the distance the arrow has to travel. So what Zeno says is that, okay, for the arrow to reach its target, it has to reach the halfway mark, right? Right, so let this be the halfway mark. So the arrow reaches the halfway mark. Now for the arrow to reach the target, and it's here, it has to again reach the halfway mark of the remaining distance. So again, it has to get to the halfway mark of the remaining distance, which is this point. And similarly now, of the remaining distance, it has to get to the halfway mark. And of that remaining distance, it has to get to the halfway mark. So even though it's getting closer and closer, you can really carry this argument out forever, ad infinitum. Every time there's some remaining distance, which is getting smaller and smaller, admittedly, but it still has to keep reaching the halfway mark. And since we can make this argument infinitely many times, it would take infinite amount of time for the arrow to reach its target. So now if you want to think about what could be wrong with this argument, where in this argument is there a flaw, since there's clearly one not what happens, what we see in reality. Now it would be a great time to pause the video and think about it. Alright, so there have been a lot of arguments, proposed against Zeno's paradox to kind of just refute it. Modern day calculus, faces many similar problems, problems of indivisibility. But let's kind of look at some of the refutations. So Diogenes, the cynic, famous Greek cynic, famously when he heard Zeno's paradox, got up of his chair, walked across the room, and sat back down smiling. His idea was that I just disproved by your idea by just showing you that it's clearly false. But again, we wanna take Zeno's argument, prima facie, and see where in his argument is a critical point that's that where he's failing, which leads him to an incorrect conclusion. Because I mean, if he's making all true statements, then the result should be true as well. But the result is clearly not true. Aristotle proposed a nice refutation, which was basically what I first thought of when I also heard the problem. And Aristotle's idea was as follows. He says that, sure, the distances, right, are constantly decreasing. For example, in the arrow case, the distances that we're halving are constantly getting smaller and smaller. But at the same time, the time, right, required to travel those distances is also getting smaller and smaller, to the point where it gets infinitesimally small and it doesn't, has no effect anymore. Now, that's a very interesting idea because, basically what the arrow version of Zeno's paradox is saying is if the total distance was 1, right, you first cover half the distance. If the distance was n, you would cover n by 2, but let's just take it to be 1, it doesn't change the calculation. You first cover half the distance, then you cover half of the remaining distance, or 1/4 of the total distance, right, which is nothing but half squared. Then you cover half of that remaining 1/4, which is 1/8, blah blah blah. So this is nothing but a geometric series with first term a equal to half, and r, the ratio that you're constantly multiplying by, the factor that you're constantly multiplying by, is also half. And we know, I might prove this in another lecture, but we know that the sum of an infinite geometric series with absolute value of r less than 1 is given by a upon 1 minus r. So this sums up to half upon 1 minus half. The denominator is also half, which is 1. In other words, this is really saying that if you sum up all those infinitesimal distances, you really get the complete distance, the entire whole distance. So you can think about it as saying, sure, you keep after covering distances, but they become so infinitesimally small after a point that the time required to cover them becomes infinitesimally small, and you just covered it for all purposes. So that, Aristotle's idea is very interesting, but there still is a little kind of there still kind of is a little empty feeling because what does it mean to say that the times have become so small that they're, you can't take them into account? They still exist, right? There's still some value. You have to take them into account. You can't just, toss them out. A small time, infinitesimally small time, is not the same thing as 0. So there's still that kind of empty feeling left. Bertrand Russell proposed another idea. What he proposed his at theory of motion, which basically says that there's no motion during an instant. And motion is simply defined as object is at A at time t1, object is at B at time t2. There's nothing happening in between. That's not our concern. And all that's required for motion is for the object to be at one point at time A and one point at time B. And when we try and extrapolate what's happening in between, we run into problems. It's something we just can't do. Just like you can't divide by 0 in math or something of that sort. Peter Linz had another argument. He basically claimed that there's no such thing as an instant of time. And his idea was that if an object is which is in relative motion, had an instantaneous relative position, it would not be in motion. Means we can't really talk about instants of time or an instant position of an object in motion. It just doesn't make sense. So these are all interesting ideas, but I mean they really do leave us feeling like something's missing, because sure, the object is motion, but I can pinpoint its position at some instant of time, right? And that idea of an instant of time seems so natural to me that you're telling me that an instant of time is meaningless is kind of doesn't gel well. Well, so that may be a valid refutation. It's very possible that we can't speak about instants of time, just like things in quantum mechanics are completely crazy. Our normal intuitions of time, space, left, right, up, down go completely haywire. But there still is that feeling that there could be a better explanation. But speaking of quantum mechanics, there's a quantum mechanics explanation as well. Basically, quantum mechanics says there is a minimum. There's a maximum. There's a minimum measurable length of space called Planck's length. You can't measure below that, and it also has the implication that there's a kind of a minimal measure of a minimal unit of space. Nothing can exist which is smaller than that length, which is shorter than that length. And Zeno's paradox relies on the assumption that between point A and point B, there are infinitely many points. But quantum mechanics may hold that that's not true, because if A and B were if the distance between A and B was Planck's length, then you really can't get shorter than that. So that could be one idea, right? When the arrow is kind of moving a Planck length distance, there's no time between getting to one point to another. So it's actually a very deep paradox, and there's a lot of kind of solutions offered. A lot of people have problems with the idea of a Planck length being the smallest unit of length possible, because then the Pythagorean theorem for the hypotenuse, you would be able to have right triangles in which the hypotenuse is equal to the length of one of its sides. Because just imagine you had Planck's length here. I'm just going to call it h. Well, and you have Planck's length here, right? And you drew a line here, a line connecting this and this, right? A line straight from here to here. You could basically build a right triangle which would have the hypotenuse length equal to one of the side lengths, which would kind of break down. But then again, a lot of our common notions break down when we get down to the quantum mechanical world. So this is a really, really deep and interesting paradox. And another quantum mechanical idea that comes out, which is called the quantum Zeno effect, is basically as follows. It's known in quantum mechanics that when you observe a system, you kind of change its state. Just like in the famous Young's double slit experiment, when an electron passes through a slit, when two electrons pass through two slits, right, they interfere to have a wave pattern on the screen. If you don't observe them, but the moment you observe the electrons, right, observe the slit, the wave function collapses and you see two dots rather than that interfering wave pattern on the screen. Again, really crazy. And the idea is that by observing the system, you kind of collapsed its state and you changed it. You changed what it does. So similarly, it's possible that by observing the system, by observing the arrow, right, by assuming that it's stopping, it has a value at some instant of time, by stopping that motion, making it discrete, we kind of change the system and lead to a nonsensical result. So, it's a really deep paradox thought of so long ago in the 400s BC, and to date it's not completely been resolved. There are very similar ideas that come out in math as well. The concept of infinity really perplexes the human mind. Infinitely big and infinitely small. Just imagine a universe that goes on forever and ever and ever in size. The human brain is almost not wired to understand that. Or infinite time. We don't really understand the concept of something existing forever and forever and forever. Because after what next? It just doesn't make sense to us. And Zeno's paradox may be a problem of infinitesimal quantities that just don't gel with the human mind. And the moment we try and analyze it, the moment we try and put our logic into making sense of it, everything breaks down. I hope you enjoyed the video. Thank you.